focus kind of on the chapter 4 review so we can get as ready as we can for Friday, tomorrow. Anything you would like to see explained or clarified? Boy, so many choices.
Did you do number 3 on the chapter 4 review?
The finding the relative extrema on the second derivative test.
Yeah.
So you got f of x 6x to the plus 15x to the fourth minus 80x to the third. So I'm trying to get you to, on this, the purpose of this is to just see if you know how to use it. But I'm saying find the relative extrema, that's the number one priority. So there's going to be a case here where the second derivative test just is inconclusive, we don't know. I still want to know then what the relative extrema is at that place. Is it a relative minimax or neither? And so then in that case you're going to have to go use the first derivative test. I don't want you to use the first derivative test if you can use the second derivative test, because that's kind of what I'm trying to get at there. So we'll start by taking the derivative and setting it equal to 0 and getting the critical points. And the numbers are awful, I would agree. So we have a greatest common factor of, I think, a 30x squared out of all that stuff. So hopefully if we can pull this out, it will get a little bit better. So that'll be x squared. That will be 2x. And that will be minus 8 to there. Does that look okay? So we get for critical points, this will factor into x minus 4, x plus 2. So our critical points are going to be 0, 4, and negative 2. So instead of doing the number line thing, which is the first derivative test, we're going to find the second derivative and then plug these points in there. So the second derivative is going to be 120x to the third plus 180x squared minus 480x. So when we plug in these points, plugging in the 0, we get f double prime of 0 is 0. So here the test is inconclusive. So we're going to, this is where I want you to come back then in a minute and do the first derivative test, but only on x equals 0. So if the second derivative is 0, it might be a min, it might be a max, or it might be neither one. So it just really totally doesn't give us any information. Now if we plug in the 4, these numbers are going to be awful, but all we really want to know is it positive or is it negative? So let's see how much we have to do to determine that. So if we have 120, and we're going to go 4 to the third, and 180, 4 to the second, and a minus 480 times 4. Are you convinced that that's going to be positive? Yeah. Just kind of looking at the size of those numbers? That's good for me. It's positive. That's all we really need to know. Is it positive or negative? So then we're going to say, because f double prime of 4 equals 0 and f double prime of 4 is positive, then 4, and now we need to know its y-coordinate, which is outrageously crazy. So hopefully ours won't be that miserable. But we're going to have to plug in all the 4s there. So you don't get to do this on the test, but I'm just going to say f of 4 is a relative miss. Okay. F double prime at the third critical point, which is negative 2, is going to be, what, 120 times negative 2 to the third plus 180 times negative 2 squared minus 480 times -2. This is not terribly clear. Hope it's negative, otherwise it's not very interesting. 8 times 120 is 800, and 8 times 20 would be 160, so is that a negative 960? That sound right?
Yeah.
Negative 2 squared is 4, 400, 320 is 720. That's going to be 980. Oh man, 960. So it's positive 2, is that what I said? Well, that's a bummer. So then you have another relative min. So this one really, yeah, I think that's still going to be.
Which one is negative?
I don't know, that was kind of disappointing. If it was negative, then we'd get a relative maximum. So here we would say, since, let me just say, because f prime of -2 is 0, and f double prime of -2 is positive, -2 comma whatever f of -2 is also a relative min. It's pretty miserable, I will grant you. Does that kind of make sense, though? So that what the second derivative test does is you take the critical points and plug them into the second derivative, because that's telling you concavity. So if the first derivative is 0, we got a horizontal tangent. And if the second derivative is positive, it's also concave up. So those two things together, a horizontal tangent and concave up, means it must be a relative min. If the derivative is 0 and you get a negative second derivative is concave down, that's going to force it to be a relative max. And the problem with 0 is that we can get an example of each of them. We can get an example of a function whose first derivative is 0 and its second derivative is 0, and it's going to be a relative min. We can also get one that's a relative max, and we can get one that's a shelf point that's neither one. And so it really just doesn't, we just don't know. So the second derivative test is just inconclusive. We can't say there isn't a relative min or max. We just don't know. We have to do something else. So then what I would expect you to do here, I guess I should come back there, is then from this one, then we're just going to do a number line only at 0. And this is going to be our f prime. So, and we got to be careful we don't go too far away, because we got critical points at -2 and 4. So when you plug in numbers here to check the sign, you don't want to drift over and pick something that's over on the other side of the next critical point, and you're getting bad information. So I think 1 and -1 work well here. If you plug in 1, we'll get, because 1 to any power is just 1, so that's 30 plus 60 is 90 minus 240 is negative. So 1 is going to be negative. If we plug in a -1, then we're going to get 30 minus 60 is a negative 30, minus 240 is negative. So in fact, this is not a relative min or a relative max. It's what we call a shelf point. So no relative extreme point at x equals 0. Or we even call it 0, 0. But I would want you to know that. So the way I phrased the question is find the relative extrema. Use the second derivative test where possible. Okay. Anything else?
Can we go over 11 in the one rule? Like all of them?
Yeah, all the ones, yeah. That's so let's take a look at these. So when can we use L'Hopital's rule? When can we not? When we use L'Hopital's rule, how do we use it? So those are kind of the questions here. So on 11, part A. So we have a limit as x goes to 0 of 2 sine x cosine x over x. Okay? Now you don't have to use L'Hopital's rule. It's just an option in certain circumstances. So any limit we try to direct substitute in first. So we plug in 0. Sine of 0 is 0, cosine of 0 is 1, 2 times 0 times anything else is 0. In the denominator, we get 0. Now, it's okay to say that 0 over 0 for your own, like, because you're checking it out. That is not going to be sufficient on my test or on the AP exam. So that won't get you any points. And if you just stop there, you will lose points. So now it is, at least in our own mind, we understand it is in the right form. It's indeterminate, but it's the right indeterminate form that we can use L'Hopital's rule. So we can say, but now to use L'Hopital and to do it right, we're going to say this is F and that's G. So we're going to show that the numerator is equal to 0 at 0 and the denominator is equal to 0 at 0. That's one of the conditions for L'Hopital's rule. So we'll say F of 0 is 0, so is G of 0. So we've checked that box that we now have satisfied the conditions for L'Hopital's rule. So now what we'll do is we will tell whoever's following our work, we're going to actually use L'Hopital's rule. So you can't just blaze on and take the derivative of the top, derivative of the bottom without explaining what you're doing. So you have to give some indication of what you're doing and the why. So now what we're going to do is, and you have to rewrite this limit again. So you can't let this limit apply to everything that follows there. And they're really picky about that on AP exams too. So you have to rewrite that limit. And now, it's not a quotient rule at all. It's the derivative of the top over the derivative of the bottom. So the top is a product rule. So we're going to take the first 2 sine x times the derivative of cosine, which is a negative sine x, plus the second, the cosine, times the derivative of the first, and the derivative of 2 sine x is 2 cosine x. Okay, that's a product rule in the numerator. In the denominator, the derivative of x is just 1. Is that okay so far? Okay. Now we're going to take the limit of this. So I wouldn't even clean things up. I would just say plug in 0. So we know sine of 0 is going to be 0. So this stuff is just going to be 0. Cosine of 0 is 1. So it's 1 times 2 times 1. So that's going to be 2. And so the limit that we got after using L'Hopital's rule is the same as the limit of the original. And that's the big power of L'Hopital's rule.
So we can't write 0 over 0 at all?
I mean, you can, but that alone isn't going to justify. So it's kind of weird because it's like they have, over the years, in the last few years, they've just tightened up what their expectations are. About 5 years ago, I graded a L'Hopital's rule question, and at that time, so that year I graded it, because I've been teaching my kids, this is what we do, show 0, 0, then go to L'Hopital's rule. So they still insisted that you say it was L'Hopital's rule. So on the problem that I graded, they said, well, we'll accept this, but we're not really very happy about it because we don't really think they are clearly demonstrating they understand what the conditions are for L'Hopital's rule. They still, you had to say that you did L'Hopital's rule and do the rest of it correct. The very next year, they had another L'Hopital's rule question on there. And there, they wouldn't give the point any longer if they said 0 over 0. And so they kind of like, it's like they're trying to tighten it up and make sure you better demonstrate your understanding. And so that's when I was like, okay, I better start teaching this. So now just saying this, you won't get the point for knowing that L'Hopital's rule applies. And so now what they've said is you have to show that the numerator function evaluated at 0 is 0. And the denominator function evaluated at 0 is 0. Then say that you're going to do L'Hopital's rule. So it's just gotten a little stricter requirements in their eyes. So this is the way I came up with to to do that as efficiently as possible, because I think it's kind of annoying. You know, to me, when you write 0 over 0, it's like, well, that's pretty clear what you mean and you understand it, but that's not sufficient any longer. So, you know, it's if you're doing this in a timed, high pressure, high stakes test, you don't want to waste time doing something that you don't have to, but this you have to. So this is the way that I think you can most efficiently say, and then, you know, if you say this, you have met their criteria. Because you're saying that the numerator function evaluated it. And if that wasn't 0, it would have to be whatever. It doesn't have to be 0. You know, these could go to 0 at 5 or -2 or something else also. So whatever that limit point is, this should make both of them equal to 0. And then you can do L'Hopital's rule. Okay?
We do B as well.
Yeah, I think we should. And C and D, right? If I understood your request correctly. So in B, what we're doing here now is the limit as x goes to infinity. So x is going to infinity of 2x e to the negative x plus 2x all over x. So, as x gets really, really big, I guess the real question is what's happening to e to the negative x? And so if we just look at this part here, you know, I'm going to pull that off to the side. So this 2x e to the negative x, as x is going to infinity, the e to the negative x is really 1 over e to the x. Okay? So really what's happening here is a separate potential L'Hopital's rule all by itself. You know, because what's going on here? You know, these are both getting huge. This is going to infinity, that's going to infinity. It could be a L'Hopital's rule. Or you could make an argument, do you remember what happens when we talk about order of magnitude of functions? Exponential is going to get much bigger, much faster than any polynomial.
Yeah.
And so it would be okay. I mean, you could do this as a L'Hopital's rule on your own, or you could just say that e to the x is a higher order magnitude function than 2x. So this limit as x goes to infinity of 2x over e to the x is in fact 0.
Wait, what?
So the e to the x is going to get much bigger, much faster than 2x. So as we put in 1,000, a million, a billion, remember if you're thinking of this graphically, you know, here's our 2x is this linear function here, but our e to the x, you know, it's taking off. So it's getting way bigger, way faster. So as you look at that fraction, this thing's just overpowering it, and it's getting to be, even though this may be a big number, this is a huge number, and the fraction is going to get really small and approach 0. So you could make that claim without using L'Hopital's rule at all. That would be okay. And then you could say, since that is going to go to 0, using this argument here, then this is going to become the limit as x goes to infinity of just 2x over x, and that's always 2. But let's just see what happens if we see it as a L'Hopital's rule problem, because we should still be able to do it that way, I think, on this one, if I remember right. So if we call this f and this g, then we're going to, we're not plugging in a number like we were on the other one. So I can't say f of infinity is equal to infinity. I have to use the limit notation. So I have to say the limit as x goes to infinity of this f. And then you're going to have to figure out, I'm not really sure what this is doing, but it's not negative. So whatever is contributing is going to be positive. And this is clearly getting huge as x goes to infinity. And so that, I'm convinced, is really going to be infinite. And then likewise, we can say the limit as x goes to infinity of g of x, our denominator function. That's clearly x is going to go to infinity as x gets used. So then this allows us to use L'Hopital's rule. So now we're back to this, take the derivative of the top over the derivative of the bottom. So again, we got to rewrite that whole limit stuff. Now here we got a product rule. So we have the first 2x times the derivative of e to the negative x. This is our chain rule applied to an exponential, e to the u. Its derivative is going to be e to the u times du. So we're going to get e to the u, that same exponential back, times the derivative of the exponent, which is negative 1. I'm just going to put it out in front. Plus the second, e to the negative x, times the derivative of the first, and the derivative of 2x is 2. Now that's just this derivative. And then we have the derivative of 2x, which is 2. And that's all over now 1. So now I feel like, we're still going to have to come to terms with what in the world happens to e to the negative x as x goes to infinity. Because that's a big part of this. And, you know, here, I think it's pretty straightforward to see that this 2, that if you understand that e to the negative x is 1 over e to the x, then as x goes to infinity, that's going to go to 0. And so as this goes to 0 times 2, that's going to go to 0. Somehow you got to still figure this out because it's not clear. You know, if you say that this is becoming an infinite and this is approaching 0, infinity times 0, that's indeterminate. Not a kind of indeterminate that we are prepared to talk about in this class, but it's one that we talk about in great detail in BC Calc. So you would have to, again, kind of come to this idea here, where you're going to rewrite that e to the negative x to make it be in the form infinity over infinity. Then we could do L'Hopital's rule, because now the derivative of the numerator is going to be, I thought you guys were right there with me. The derivative of the numerator is going to be just 2. The derivative of the denominator is incorrect. So if we, at least in our head, do a L'Hopital's rule here, now as x goes to infinity, that's going to go to 0. So this, somehow or another, you have to come to terms with what is happening to this 2x e to the negative x. Whether you do it right off the bat in the original, or at some point in time after you've started L'Hopital's rule, you still got to address that. And then that's going to actually go to 0. And so we're going to get 2.
So on the test, do we have to use, you know, the rule?
No, L'Hopital, easy for you to say, huh? No, I mean, L'Hopital's rule is just one more tool in your toolbox.
Okay.
It is not the be-all, end-all. And people get in trouble when they try to use L'Hopital's rule on every limit problem that comes up, because it isn't always the most efficient, and a lot of times it just doesn't work. It only applies if you have 0 over 0 or infinity over infinity. And people try to, a lot of times, apply it in cases where that isn't happening, and then it's wrong right from the get-go. But a lot of times it just isn't the best way. But it can be really useful when you can't figure anything else out. Okay?
Can we still figure it out without using the L'Hopital?
Absolutely. Absolutely. That's the way I would approach this. But, you know, I've done a few limits, and so I'm not sure we're in the same place. Because when I would have done this right from the beginning, because I'm pretty familiar with this, I would have thought this through in my mind and said that because this e to the x is a higher order magnitude function than 2x, a polynomial, what's happening is it's going to 0 faster than that's going to infinity. And so the result is it's going to drag that to 0 with it, and that's just going to go to 0. And then we're just at 2x over x, and that's going to be 2. And I would not have used L'Hopital's rule on this problem at all myself, but I don't know if everybody's in that same place. So it's just more options. You know, the more ways you understand something, the better off you are. You're just a much better place. Is that okay? Let's see, I think we're up to C, right? Okay. So C is now limit as x goes to infinity, 6x over x plus cosine x. Okay, so as we look at this and say, as x gets huge, the numerator is always 6. The denominator, what's that? Is it 6x?
Yeah.
That makes it more interesting. It was too easy. Okay. As x goes to infinity, this is going to go to infinity. This is getting huge, plus cosine x, which is, yeah, it's not really going to 1, but it's not really going to anything, because it's just going to keep doing what cosine does. So at various choices of x, it's going to be sometimes as big as 1, sometimes as small as -1, and all numbers in between. But it's not getting closer and closer to a single number. But on the other hand, it's not growing large without bound either. So, what do you think? That's what I would do. That's what I would do. So if you realize that as x goes to like 1,000, a million, a billion, when you add whatever cosine of x is, that's at most 1 and at least -1. A billion plus 1 or minus 1 isn't going to make any difference. And this is going to be, so this is going to act like just 6x over x. And that cosine x isn't making a significant contribution, which means the limit is going to be 6. And I wouldn't use L'Hopital's rule at all. Now let's talk about what if you did, because you may not have seen through it. Now if you did say that, you know, this is f and this is g, and the limit as x goes to infinity of f is infinity, so is the limit as x goes to infinity of g. Then you would say, okay, let's do L'Hopital's rule. And so now we're going to get the limit as x goes to infinity. Now that's going to be 6 over 1 plus, yes, the derivative of cosine is a negative sine x. Now, this is worth talking about because as x goes to infinity, this 6 is just always 6. This 1 is always 1. What's happened to the sine x as x goes to infinity? It's oscillating around here. So if we are saying, if we were going to graph this and say what is happening as x goes to infinity, we're going to see that, you know, if this is 6 and we're going out here, sometimes when sine is 0, we're going to get just 6. Sometimes when sine is positive, well, when sine is -1, we'll get 1 minus the -1 is 2, 6 divided by 2 is 3. So we're going to drop down as low as 3. Now it gets wacko when sine is going to be +1 because now it's not going to be defined. Right? Because 6 minus 1 is 0, dividing by 0 is undefined. So every time sine is equal to 1, for all these values of x going out to infinity, we're going to get a vertical asymptote. So you're going to be talking about it's going to blow up on one side and blow up on the other side. And then a little bit later it's going to blow up and then it's going to... So as you look and say, well, is this getting closer and closer to a single number? The answer is no. So then that means the limit does not exist. And this is the kind of like the part of L'Hopital's rule that, you know, people don't really pay much attention to because they're so focused on, can I use L'Hopital's rule? Is it 0 over 0? Is it infinity over infinity? Oh, it is, great, I can use it. Then they'll say, oh, this limit doesn't exist, therefore the original limit doesn't exist. That's not true. But L'Hopital's rule says if the resulting limit doesn't exist, then L'Hopital's rule does not apply. It just isn't a technique that will work on this problem. Go back to the beginning and figure out a way to decide what this limit is without using L'Hopital's rule. And that's a part that most people don't really understand about L'Hopital's rule. So when this doesn't exist, then L'Hopital's rule does not apply. So we know nothing. We know we are no better off than we were in the very beginning.
So when you say if you see cosine or sine and x goes to, or the one that goes to infinity, you just say like ignore L'Hopital's rule?
I hate to make a blanket statement like that because there could be some way that might come into play. So I think very likely L'Hopital's rule is not going to work because a lot of the good examples that are accessible where L'Hopital's rule does not work involve things like this where you've got a sine or a cosine.
Okay.
Because as you go to infinity, sine and cosine aren't getting closer and closer to a number. So if they end up, after you differentiate it, getting it paired up with just a constant, it's not going to approach a single number. Where if it's paired up with something that's going to get huge, then this just means you can ignore that because it isn't making a significant difference. Does that kind of make sense?
Yeah.
I hate to make a blanket statement because it could be something I'm not thinking of that might not be the case. Great questions. Do we have one more to do?
Yeah.
All right. So in D, we have the limit as x goes to 0 of 1 minus cosine squared 2x all over x squared. Okay, so we try direct substitution. That's where we always begin. If we plug in 0, we get 2 times 0 is 0. Cosine of 0 is 1. 1 squared is still 1. 1 minus 1 is going to be 0, and 0 squared is 0. So it's certainly a candidate for L'Hopital's rule. Should we give that a shot? Why not? So we'll call that F. We'll call that G. We're going to say the limit, I'm going to say not limit here because it's not infinity. F of 0 is 0, so is G of 0. We've checked that box that we need to. L'Hopital's rule does apply. So we are going to communicate that we're going to use L'Hopital's rule. I'll take the derivative of 1, that's 0. You take the derivative of negative cosine squared 2x. How does that work?
Triple chain.
It is indeed. So we have a 3-link chain there. 2x inside a cosine inside a square function. So starting with the derivative of the square, that's going to be negative, because the negative's still there with it right now. So a negative 2 cosine to the first of 2x. Now we're to the cosine level. The derivative of cosine is negative sine of 2x. Now we're to the 2x level. Its derivative is 2. I'll do the bottom. Okay. All right, so now we're going to take that limit as x goes to 0. Let's see. Cosine of 0 is 1, but sine of 0 is 0. So that's 0. That's 0. We have 0 over 0 again. You can do L'Hopital's rule again.
Oh, no.
Okay, so now here, I don't know a great notation. Do we want to just say this is f prime and this is g prime, because that's where we got them from? Or do you want to call them something else, h and k, or whatever you...
That one makes sense.
It kind of makes sense, I think. So now we can say that f prime of 0 equals 0. So does g prime of 0. So it meets the criteria for L'Hopital's rule because the numerator function is 0 and the denominator function is 0. So we're going to use L'Hopital again. Okay. Well, let's clean this up a little bit. I'm going to call it 4 cosine 2x sine 2x. So now we're going to do a product rule again. So we have the first, that's the 4 cosine of 2x, times the derivative of the second. So that's the derivative of sine 2x, which is going to be 2 cosine 2x, plus the second, the sine of 2x, times the derivative of the first. So there's going to be the 4 times the derivative of cosine, which is negative sine 2x, and then we get yet another 2. Is that okay? All over, I got the denominator 2. Well, this is good because we're not going to get 0 over 0 anymore. And we're going to take the limit. Let's not forget to write this if we've done so well. I wouldn't clean things up at this point. I'd just plug in the 0 and see what's going to happen. Cosine of 0 is 1. There's another cosine of 0 is 1. So that's 4 times 1 times 2 times 1. That's going to be 8. There's a sine of 0, which is 0. All that stuff's wiped out. It's gone. It's going to be 8 over 2, which is 4. That's our limit. So you can do L'Hopital's rule repeatedly until you get some kind of resolution.
Can I go over this?
And then after that, we'll follow also to the limit.
That's the one that is,
Yeah, okay. With the L'Hopital and the limit, we have to write L'Hopital.
Yeah, so yeah, and that's the thing. Every time you get to a new limit, you got to rewrite it again. Yeah, otherwise they'll ding you.
So if the limit was to infinity, is that when you would say it would just be 1 over x squared? Or is that how that works?
Yeah, well, here actually, so as x goes to infinity, up here, you know, it's kind of bouncing around a little bit, but it's not getting large without bound. So for some choices, this might be 0. Other choices, it might be something between 1. This will, because it's squared, we'll never get a negative out of this. But it's not growing large without bound. Meanwhile, this is blowing up. So it's going to approach 0. It'll approach 0.
Oh, okay, I got you.
Okay, so whatever this is doing, this thing is overpowering it. So it's going to still approach 0. Does that help? Anything else?
if no one else has a question.
Yeah, make it yours.
We can do 6.
6. Okay, now this is going to be a bit involved, all right? So if it's real involved, probably you wouldn't see something like this on a test question, right? I wouldn't bank on that. I got a feeling that you're going to do something like this. So we have y equals x over x squared plus 1. So we're going to use all of our calculus to figure out what the graph of this looks like. So that means I want you to do everything, get all the information you can from the first derivative, all the information you can from the second derivative. I think there might be a horizontal asymptote in here, and then we're going to put it all together and get a pretty accurate graph. So maybe we'll do that right off the bat. Limit as x goes to infinity of this function. As x gets really, really big, what's this thing going to approach? 0. Does that make sense? Because the degree of the denominator is bigger than the degree of the numerator. So that means we're going to get a horizontal asymptote at y equals 0. Okay, now we're going to get everything we can from the first derivative. So I'm just going to refer to that as f, so maybe I'll name it so there's no question. So this is going to be a quotient rule. So we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Is that okay? Okay, tell me if I'm just going too fast. I'm going to clean up the numerator. So that's going to be x squared plus 1 minus 2x squared over that x squared plus 1 squared. So that's going to become a 1 minus x squared in the numerator. X squared minus 2x squared is a negative x squared. Okay, now this is a nice form, believe it or not, for our derivative. So when we're looking for critical points, yeah, that didn't look very nice to you, huh? So when we're looking for critical points, we want to know where is the derivative 0 or undefined. So that becomes two separate questions when we have a single fraction. This will be equal to 0 where the numerator is 0. This will be undefined where the denominator is 0. So if we take the numerator and set that equal to 0, we're going to get positive and negative 1. Those are critical points. Now, if you try to take the denominator and set that equal to 0, you can see that no matter what you plug in for x, once you square it, it can't be negative. So it's either going to be 0 or positive, and if you add that to 1, there's no way that's going to be 0. So this is not going to be equal to 0 for any choice of x. So there are no critical points that come from making the derivative undefined. So these are only choices, 1 and negative 1. So we'll do our number line. I'm going to call this f prime. There's negative 1, there's positive 1. Now we're going to plug in the signs. And this is tricky, especially when it's all new. So we have to kind of learn some good strategies. If I plug in something like negative 2, then 1 minus negative 2 squared is 4. 1 minus 4, the numerator is going to be negative. Now the denominator, no matter what we plug in here, once we square it, it's positive. So for the whole, all the other numbers we test, the denominator is always positive. So negative over positive is a negative. If we plug in 0, 1 minus 0 is positive. So we have a positive over a positive, that's going to be positive. I plug in 2, 1 minus 2 squared is negative again. So now we have a negative over positive, we're back to negative. So if, and I don't know if it asks for intervals. I think of one of these I asked for intervals where it's increasing, decreasing, and the other one I just said use that information. So if we were going to write the intervals, we would say it's decreasing for x less than or equal to negative 1, and for x greater than or equal to negative 1, and it's increasing for negative 1 less than or equal to x less than or equal to 1. You'd include the endpoints. If they don't ask, we'll just use this, but not have to write it down. But we do see where it changes sign here. So that means we're going to get some relative extrema. So we have a relative, since it goes negative to positive, our function goes decreasing to increasing. That's going to be a relative min. And remember, you always have to get a y-coordinate to go with that. Y-coordinates always come from the original function. So we're going to plug negative 1 back into the original. In the denominator, negative 1 squared is 1, plus 1 is 2. Negative 1 over 2 is a negative 1/2. It didn't ask to justify, so I don't have to say it's a relative min because the derivative changed from negative to positive, but I know that, and if we were asked to justify it, we could say that. We see it goes positive to negative, that's going to make it be a relative max. And so again, we're going to plug in the 1, and this time we get a positive 1/2. Okay, that's all we got from the first derivative. So now we switch to the second derivative. So now we're going to find f double prime of x. So here we are, here was our derivative. So I'm looking at this, and now we have another huge quotient rule. No way I'd ask you something like this, right? I wouldn't bank on that. Denominator times the derivative of the numerator. That's going to be a negative 2x. Minus the numerator, 1 minus x squared times the derivative of the denominator. And that's going to be a quotient rule. So we have 2 times the x squared plus 1 to the first times the derivative of the inside function. There's a 2x all over the denominator squared. Do not multiply that numerator out. And it becomes hopelessly complicated. Factor. So we have a common factor of x squared plus 1. So we're going to pull that out. We also have, and it's your choice, do you want to pull out a 2x or a negative 2x?
Negative.
Negative 2x. So let's see what that leaves behind. This is where you really learn algebra, is in calculus, because there's a lot of algebra. So we took out one of the x squared plus 1s. There's still going to be an x squared plus 1 left. And we decided, because Miranda wanted to take the negative with it, that negative 2x is gone. It's all the way out. Okay, now, we took out this x squared plus 1, and because we took out the negative 2x, we took that negative with it. That's now a plus. And we still have 2 and a 1 minus x squared. And that's all over our x squared plus 1 to the 4th. You okay? All right, now we can cancel this x squared plus 1. This negative 2x we're going to leave hanging out there. Don't forget the x part. The negative 2x is hanging out. Inside the brackets, we're going to distribute combined like terms, see what we get. So we got that x squared plus 1 plus 2 minus 2x squared. Does that look right? So that's going to be a 3 and a minus x squared. 3 and a minus x squared over what's now x squared plus 1 to the 3rd. This is our f double prime of x. Good. Okay?
Yeah.
Now we're looking for pips, potential inflection points. So just like we did with the first derivative, we want to know where's the numerator 0 and where's the denominator 0. Well, we already made the argument the denominator is never 0 because x squared plus 1 can't be 0. So that makes it easier. Now we're saying negative 2x times 3 minus x squared is equal to 0. We want to solve that.
Should be positive and negative square root of 3 times 0.
You got it. So positive and negative square root of 3. You see where she's getting that from? And the 0. These we call pips. They used to run around with Gladys Knight. I don't know how old you are. You're probably not old enough. So those are potential inflection points. Okay? Now we got to do what we did with the first derivative on a number line with the second derivative. So I'm going to, I like to kind of have them right there next to each other. So we still remember we got y equals 0 is our horizontal asymptote. Let's not forget that. Here's now going to be our second derivative. So 0 is going to be right here. That's a pip. Square root of 3 is bigger than 1, so it's going to be more over here. And the negative square root of 3 is going to be there. You with me? So square root of 3 is less than square root of 4. So square root of 4 will be 2, so a negative 2 is over here to the left. If we plug in a negative 2, the denominator is always positive. Negative times a negative is positive. 3 minus negative 2 squared is 4. 3 minus 4 is negative. Positive times negative is negative. We have a negative over a positive, which is going to be negative. Square root of 1 is in between 0 and square root of 3. So I plug in negative 1. That's still negative. I'm sorry, that's still positive because negative times negative. But now negative 1 squared is positive 1. 3 minus 1 is now positive. You got positive, positive, positive. That's now positive. Plug in a positive 1. Now a negative times a positive is negative. And 1 squared is 1. 3 minus 1 is still positive. Negative, positive, positive is negative. Put in our positive 2 that's out here. So negative times a positive is negative. Positive 2 squared is 4. 3 minus 4 is now negative. Negative, negative. Positive is positive. We're going to go there. So we know where it's going to be concave up, concave down. And we can see there are 1, 2, 3 places where the second derivative changes sign. That's 3 inflection points. We need those. And their y coordinates are going to come from the original function. So we plug in a negative square root of 3, and we're getting negative square root of 3. Negative square root of 3 squared is 3, plus 1 is 4. So it's a negative square root of 3 over 4. Okay? Plug in 0. 0 over 1 is 0. So we've got 0, 0 is going to be an inflection point. Plug in positive square root of 3, and we get square root of 3 over 4. So that is also, so what did I see? Square root of 3, square root of 3 over 4 is going to be another inflection point. Okay. You can start the drum roll now. We're ready to graph it. So let's remember we have a horizontal asymptote at y equals 0. That's easy to forget because that was a long time ago. Okay. Let's plot the points that we know. We have a relative min at -1, -1/2. That's going to be right there. And we have a relative max at +1, +1/2. We've got an inflection point at 0, 0. That's easy enough. Negative square root of 3, negative square root of 3 over 4. Oh, good grief. This is like about 1.7. So a negative 1.7 is going to be right in here. And 1.7, negative 1.7 over 4 is not quite to -1/2. So it's going to be right in about there. I'm just going to change concavity. That make sense? And then, let's see, here's 2. So square root of 3 is going to be in here. And square root of 3 over 4 is going to be not quite to 1/2. That's square root of 3 comma square root of 3 over 4. Okay, so we'll go too fast. Okay, so it's going to be decreasing and concave down until we get to square root of 3 here. So and it's going to approach that asymptote. So decreasing, concave down to there. Then it's going to continue decreasing until we get to -1, but now it's changing the concave up. So it's going to be something like that. Okay. Now increasing, and now we have switched to concave up. So it's increasing concave up till we get to 0. Now it's going to be, oh, that's my second group. Increasing concave down until we get to 1. Increasing concave down. Then after 1 is going to be decreasing and still be concave down till we get to square root of 3. Decreasing concave down. Continue decreasing the rest of the way. Continue being concave up and approach the horizontal asymptote. Crazy.
With the f prime, when we're finding the 0, if you could have gotten a 0 out of the denominator, that would have been vertical asymptote, right?
Correct.
Okay.
Yeah, well, that would have been in the original function, yes. I think we're just doing evens, right? So I don't need to give you a new worksheet. Is that what I have for today? Okay. Test is tomorrow at 8. Make sure you bring your notes with you. I'll be here after school if you want to do any extra practice.
I'll be there after.
Okay. All right. It might be two people here. Okay. Okay.
So I could come in after school today and take it?
Ready for it?
I think so.
Oh, just word of warning, it is long, it is difficult, don't panic. There's a 10% curve on it. So
Oh my God.
just if you get stuck on something, let it go, make sure you answer all the ones you can answer, then come back to the ones that are gonna be difficult, because there will be some.
And then I just want to remind you that I'll be taking 3.6.